Here is an introduction to inflation to accompany chapter 29 of the textbook Astronomy from Open Stax. So before I get into what inflation is, it's just a very rapid expansion of the early universe. Why would we need this? Well, when we look at the cosmic microwave background, which we talked about in the Introduction to Big Bang lecture, you see that it's extremely uniform. We can look at the density and the temperature perturbations, and they're very, very small. It's almost too uniform, right? So the issue that we have is that the regions on one side of space are very similar to regions on the other side of space, right? So if we look one direction from the Earth and we turn around and look the other direction from the Earth, the things are very uniform. They're extremely similar in structure, extremely similar in temperature. There seems to be very little variation. And how can we really explain that? So if the two regions were somehow in communication, or were in communication at one point in time, you would expect that sort of similarity. So for instance, if a photon traveled from one region to another, that can communicate some kind of energy, right? It brings energy from one region to the other, and these regions can kind of homogenize to some extent. The issue is that when we're sitting here on the Earth and we look out in one direction, the furthest away we can see, the horizon of the observable universe, is the photon travel time, basically, from the furthest extent. So a photon began traveling at the beginning of the universe around 14 billion years ago, and it travels to us and we can see that. But we can look in the exact opposite direction, and again, there's some photon that began traveling 14 billion years ago, roughly, and it reaches us. And these two opposite extents of space could not have communicated because they're outside of this photon travel time from each other. So how do we have this uniformity then that is that we observe? The Big Bang theory doesn't really account for that. So they didn't communicate. How are they so similar? So the solution to that is, well, maybe they did actually communicate. Maybe the early universe was extremely tiny, even smaller than we predict from the Big Bang. And rather than expand at the extremely rapid rate we would think happens for the Big Bang, what if it expanded even faster than that? So this tiny point in space things were communicating. There was an extremely rapid expansion, and so there wasn't really time for anything to change much. So they communicated via photon exchange and particle exchange. These regions then became very similar. There was an extremely rapid expansion, and there was no time for them to become very different. So then the universe, no matter where you look, looks relatively uniform. There's similar structure, similar density, similar objects. So that is a possibility. This theory is known as inflation. And I call it a possibility because, as I'll mention, inflation, there is no direct evidence for it whatsoever. It is a compelling explanation, and that's why we're bothering to talk about it in this class. So visibly, or as pictorially, this is what we're talking about with inflation. At extremely early times, everything starts out as a really, really tiny point. This is a log scale here. These distances are just, ridiculously small. Everything's very compact. And then, in an extremely short amount of time, boom, everything expands 40 orders of magnitude in size. Still extremely small, okay? So you're still not talking about too big of a length scale, but just a more or less instant expansion. So things have time to communicate and homogenize, and then there's a huge expansion, and they haven't had time to change much. So it's all very similar, and then you proceed with your standard Big Bang. So another reason that we find inflation compelling is not only that it explains this sort of homogeneity of the universe and just very similar structures everywhere, but there's also this issue of curvature of the universe. And this gets a little bit complicated because we can visualize curvature of a 2D object in 3D space, but of course space is already 3 dimensions, so visualizing it is kind of bends your mind a little bit. But let me give it a go here. So space-time, this is the spatial and time coordinates of our universe, right? So at any given point in time, that's one time coordinate, and some volume of space, those three dimensions are the spatial coordinates. And this can actually, space-time can be warped, and it is warped. For instance, when you place a massive object in the fabric of space-time, it is bent. So this is a 2D representation of what's happening in 3 dimensions, but if you take your Earth, it is sitting in space-time, and it is warping space-time locally because there is a large gravitational force due to the large mass of the Earth. And one way we can think about why, for instance, a satellite orbits the Earth is, it's attracted by the gravitational potential, and that is what is keeping it in orbit of the Earth. Another way you can think about it is that satellite is kind of riding in the gravitational potential well, so it would be following one of these circular contours. It's kind of like if you've ever gone to the mall, if people do that anymore. There are those sort of swirly coin things. You put your coin in and your coin rolls around the rim for a while until it goes in. Well, the reason that it rolls in eventually is friction. If you're out in space and there is no friction, then your coin or your satellite will just roll around. And it's rolling around here in this warped fabric of space-time. So for instance, for a satellite going around the Earth, you could also draw something similar for the Earth going around the Sun, or the Sun going around the center of the galaxy. So this is a relatively well understood phenomenon as described by general relativity. Now, in principle, our universe, the visible universe, which I'm going to call the local universe, it could also be warped or curved in a kind of similar way. So we call that a curved space-time. But it turns out that it isn't. And that is showing that that's the case is a bit complicated. You're going to have to go take upper level astronomy. But we can see from the cosmic microwave background that space-time is flat. It is not curved when you take a look at the visible universe as a whole. And so one way to kind of neatly explain this is inflation. So the idea is that in principle you could actually have curvature of your very early space-time. But if everything expands very rapidly, then all your material, the visible universe, is actually localized on a very tiny point of this curved space-time. So imagine all of the universe, whatever that is, as this balloon, and this ant as the entire visible universe. If you're this little tiny object, then when you're near the surface looks pretty flat to you, right? So the idea of inflation is that the universe expanded to this huge thing. The visible universe is teeny tiny, and so to us, regardless of what the true curvature of all of the universe is, whatever all of the universe means, the stuff that we can see is always going to look flat for any observer in the visible universe. Now, I've mentioned the basic theory of inflation, or at least the consequences of it. So what's the proof that this happens? There isn't any. There is no direct proof. There's only circumstantial evidence, right? So the circumstantial evidence is this is a cute way to explain the flat space-time, and it's a cute way to explain the relative homogeneity of the universe and the sort of similar structures, sort of no matter where you look. So you can think of it as kind of the best of bad options. There isn't another theory, or not one that I'm aware of, that at least is supported by circumstantial evidence. Now, it would be a useless theory if there was no way to prove it or disprove it, right? That's junk. At that point, you're just talking about philosophizing, right? There's no point in going deeper there. The nice thing about inflation is it does have testable predictions. It just has been to date extremely hard to actually make the observations needed to test the predictions. So one potentially observable signature that we have is we can look at polarization of light from the cosmic microwave background. So you may remember from the introduction to light lecture that light can be described by electromagnetic waves, and any given photon can be treated as something with an electric field and a magnetic field, and the strength of these fields are oscillating in time. So they're increasing or decreasing. And when you make this picture here, this particular photon is oriented in one particular direction. So the electric field strength increases up and down and up and down, and that's it. And so this photon here is polarized. So if all of the light from a light source had this same polarization, the electric field oscillating up and down in this particular direction, that would be a polarized light source. What you usually have instead is something like the sun. This orientation is different for every photon. So some of the photons, the electric field is up and down, up and down. Some of them, it's going to be in and out of the page. Some of them, it's going to be diagonal, and kind of any orientation you can imagine can occur. So that would be a non-polarized light source. But light can often be polarized by different interactions. And so, for instance, sunlight scattering off of a smooth surface, like for instance a pond or a puddle of water on the road, that light winds up getting polarized. And this is actually how polarized sunglasses work to reduce glare, is they filter out light with a given polarization. So light where the electric field is oriented in a particular direction. So believe it or not, polarization is something you deal with kind of all the time. So what does this have to do with inflation in the cosmic microwave background? It's a bit complicated to explain, but basically we expect a particular polarization pattern of the light that we observe in the cosmic microwave background if the inflation theory has actually occurred, if it's correct. So there are two main kinds of light polarization that we can have. This one is called an E mode. This one's called a B mode. What you're looking at here is literally kind of two-dimensional space. So if you looked out at the cosmic microwave background and you're looking at some rectangular slice, okay, and then at each point in space you're saying which way is the light polarized. And in this chunk of space, light's polarized that way. In this chunk of space, it's polarized this way. And this particular E mode polarization that we have here, this is what is expected from just local density perturbations. The inflation theory, part of the prediction is that there are these ripples in space-time from gravitational waves due to inflation. And these ripples in space-time, a consequence of that is a B mode polarization. So if you looked at the same chunk of space, instead of seeing light here polarized that way and light here polarized that way, the polarization direction, relatively speaking, is different. So you have kind of these swirls. You notice the polarization direction swirls around for the B mode, whereas it just is radial for the E mode. So what we're trying to observe, or what some people have tried to observe, is the signature of this B mode polarization. If you could see this signature in the cosmic microwave background, you would have potential proof for the inflation theory. Now this signature, this B mode, is extremely faint and hard to observe. There was a false alarm a few years back, a handful of years back, where it was believed that this polarization had been observed, and we thought, hey, inflation theory has direct evidence. That turned out to be a mistake, observational error. So to now, there is no direct proof for inflation. And it gets worse. So how does inflation theory work? That's a very good question, and you should keep asking good questions. There's not a great answer, so I'll give you the only answer we can give. We don't really know. So the problem is that when you take such a huge amount of matter and you compact it into such a small volume, you have extremely high densities, and so you need gravity. But you have extremely small scales, and so you need quantum mechanics. So the strong force, the electromagnetic force, and the weak force. You need these to be in there. The problem is there is no theory that links these, that unifies these. So our theories break down at those scales, and so we have no way to describe with the physics that we have now what's going on for something like that in the universe, such small scales and high densities. So we can take a look at our fundamental forces. There are 4 forces that we can describe the whole universe with. The strong force, this describes nuclear reactions. The electromagnetic force, this describes light, electricity, magnetism. The weak nuclear force, this describes radioactive decay. And then gravity, which describes the interaction between massive bodies. So we have four separate theories here that work, at our current universe. And these can be unified. So for instance, the electromagnetic force, this is actually already a unified theory. So if you go back a couple hundred years, electricity and magnetism were separate phenomena, and at one point they were unified into the electromagnetic theory. So we can describe those together. More recently in history, the weak nuclear force describing radioactive decay and the electromagnetic force, these have been unified by the electroweak theory. So we can describe, with the physics we have now, at some early time in the universe, when these two forces were essentially indistinguishable, we can describe that with current physics theory. The problem is when you go earlier in the universe at hotter temperatures and higher densities, we don't have any way to link these other theories with these two. So there are people who are working on a so-called grand unified theory, and there are many different attempts at this. And the grand unified theory, this is something that would link the strong nuclear force to the electroweak force. No successful theory exists yet, so we can't describe the universe at this point in time when these would be linked. We can't go any further back. If we want to go to inflation, to the very beginning, we really need a theory of everything. We need to not only link the strong force to the electroweak force, we need to link that to the theory of gravity. And so this is a theory that would explain all four fundamental forces in one coherent framework. So an example, an attempt at this is something called superstring theory, but I want to emphasize there is zero proof for any grand unified theory or gut or a theory of everything, a toe. There's just no direct evidence that these exist. And if we're honest with ourselves, it's possible that there may be no such unified theory. We want to believe that that there are such unified theories, that the universe can be described in an elegant way. But perhaps the universe isn't elegant, and maybe no such explanation exists. So, as a Russian professor of mine used to like to say, it's not good to wish for something too strongly. So, perhaps guts and toes, there is a gut and there is a toe, perhaps, but perhaps not. And so right now, when you're looking at the different options on the market, we should keep in mind the words of Shakespeare that there's small choice in rotten apples. And by that we mean, you can't really distinguish between one of these guts or toes and the other, because the fact of the matter is there's not really any strong evidence for any of them. So, if you decide to go into astrophysics theory, or I guess this would really be more particle physics theory, perhaps you will come up with this theory and solve this problem. But for now, no one's been able to do that. And that is it for this introduction to inflation for Astronomy 1000.